We started lesson 3 by getting into groups and looking at the jump start. Which one doesn't belong? And really, any of these could have been the answer. It depends on the reason. So, for example, A is the only one with 2 primes with exponents. If you view 5 as having an exponent of 1. B is the one that has 2 written with an exponent. C is the only one with a fraction. D is the only one without any exponents, and those are composite numbers, or the opposite of prime. And E is the only one with 4, so 4 factors, that is. So really, it's there's not one answer. It just depends on how you look at it. So now in today's launch, we looked at this. It looks very familiar to us. It's a variation of what we did before. It's a triangle. I hope that's obvious to you. It's a triangle. And at each of the corners, it's increasing. But how is it increasing? Well, it's increasing by doubling. So 1 doubles now to 2, and that 2 doubles to 4. Each of the corners is, each of the corners is doubling. And so the question is, and number 1, how do you see it growing? There are a couple of ways you could look at this, but basically your description should mention the fact that the pattern is doubling at the corners. And of course, labeling the pattern. One of the suggestions that I make in class is that you really should, if you're stuck, count. Put the numbers on here. So at the beginning, there was 3, and then 1 minute later, there's 6, and then 1 minute after that, there's 12, then 24, 48. So what about this next figure over here? Well, that's what the next question asks you. And if we're doubling, double 48 is 96. So there was 96 that were here at 5 minutes. Now, when we model this, when we use our tools, our tables, our graphs, our equations, we can really get some insight into how this thing is building. Okay, so for the table, let's say, let's not even use X and Y. Let's just say it's an input-output table. Okay, so our input is 0, our output is 3 dots. Our input is 1, output is 6. 2, 12, 3, 24, 4, 48, and finally 5, 96. Let's just take one of these lines of the table and sort of figure out where that number came from. So we said that you're doubling as you go along. Doubling means to multiply by 2. But you have to have a starting place. You can't just start doubling nothing. Even 0 is a number. So what are we starting at? We're starting at 3. So by the time we get down to 96, so we've started with 3 and we've doubled it. But how many times have we doubled it? Well, let's count them as we go down. 1, 2, 3, 4, 5. 1, 2, 3, 4, 5. 5 doublings of 3. And of course, what would be the shortcut way to write that? Well, that 96 would be 3 times 2 to the 5th power. So in other words, the exponent matches the step number that we're on. So if we use t in our table, we want to go and generalize. How about 3 times 2 to the t? That certainly would work. So if I was to set that equal to a letter, I don't want to use capital T again because capital T, lowercase t, that can be confusing. So let's just say it's S. S for sum. The sum of all the dots is 3 times 2 to the t. Now, you might think that the recursive equation is the most difficult, but actually, in this case, it's the most easy because the next one, well, how do we get the next one? Doesn't it come from doubling the one that came before? And that's just 2 times previous. Last thing for the graph, and I'm going to have to do a little erasing here because I spilled over. We do not have to use 1 square equal to 1 number. In other words, we could do 1 for 1 here. We could say that that's, 1, 2, 3, etc. But we could even do this. We could say, let me back up a little bit. We could say 2 squares is equal to 1. 2, 2, 2, 2. So this could be 1, 2, 3, 4. And we'll go one more, 5. Going up, nobody says that 1 squared has to equal 1. We could do what's ever convenient to us. So, for example, we could do every 2 squares is worth 10 going up. And even then, we don't have to label each and every one of them. So we could say that this is 10, 20, 30, 40, 50, and so on, all the way up. We may not even get all of our dots on here. That's fine. But you take a look, and we had 0, 3, it's right about here. 1, 6, right about here. Oops, I put that in the wrong place, didn't I? 1, 6. 2, 12. And then it really takes off. 3, 24. 4, 48. And 5, 96. So is that a straight line? No, it's not. So remember that. When you have this multiplying pattern, you do not get a straight line in the graph. Well, that's it for now. This is a nice problem. We didn't have time to do it in class. But we'll go ahead and talk about a few of our takeaways. A geometric sequence is what we worked on today. And geometric sequences are for multiplying. We used a table, we did our explicit equation, we did a recursive equation, we looked at the graph. In fact, we could use a function for our explicit. I could say, for example, instead of s equals, I could say s of t equals 3 times 2 to the t. And that would be more in keeping with what we learned last week. And notice under our vocabulary here, that common ratio, that's what we kept multiplying by over and over. In our case, that was the number 2. And the change factor was 2. 2 was the number we kept multiplying by. And one other number that sort of came up in the early part of the lesson was prime numbers. If you don't remember what prime numbers are, they are numbers that can only be divided either by 1 or their self. So first prime numbers from 2, then 3, 5, 7, 11, not 9, because 9 is 3 times 3, 13, 17, 19, and so forth. So we'll see you next time for the Ready, Set, Go.